we are the only intelligent life in the known universe.
I mean, imagine that we're the only place where there is intelligence in this galaxy.
It is our largest collider in the world.
CERN blew the world up in 2008.
Deep underground, Satan is drawing near, and it's all thanks to the European Organization for Nuclear Research, located on the border between Switzerland and France. Here, the Large Hadron Collider sends particles racing around its 16.8-mile track, colliding them at near light speed. All findings are kept behind closed doors at this European organization. Why are all the scientists trying to cover up this big mistake? Let us explore the horrible discovery that could instantly warp our planet to another galaxy. The darkest quest at the heart of physics. The Large Hadron Collider hosts several detectors, each named and designed for specific types of experiments. ATLAS and CMS are designed to look for a wide variety of particles, including the Higgs boson, a particle believed to give mass to other particles. ALICE looks back in time to the Big Bang by studying a state of matter called quark-gluon plasma that existed right after the universe began. Despite its scientific goals, the Large Hadron Collider has been a subject of debate. The machine involves a huge financial investment and complex technology. For every new discovery, there are endless hours of setup, data checking, and analysis. This raises questions about whether the scientific findings are worth the enormous costs and effort. The Large Hadron Collider is like a huge bet, hoping that the answers found by smashing tiny particles will reveal new truths about our universe. When particles collide at high speeds, they break apart, potentially revealing parts or particles that we don't usually see. The detectors around the collider capture this process, providing valuable data. This data helps physicists figure out the forces that hold everything in the universe together. Essentially, it's like asking nature very detailed questions and seeing how it responds, using the tools and language provided by physics. But the Large Hadron Collider is as much about generating new questions as it is about answering old ones. Every discovery seems to lead to further questions, keeping scientists busy with new theories and more experiments. This constant cycle of questioning and testing is fundamental to science, but it also means that there is always more to learn. Critics often wonder if all this effort is sensible. The cost of running such a huge machine and the complexity of the experiments make some question if this is the best way to explore the universe's laws. As discussions continue in academic and research settings, the value and impact of the Large Hadron Collider remain topics of ongoing debate. This exploration is essentially a continuous loop of exploring, discovering, and then seeking to understand the new information, which often complicates previous understandings. The process is demanding and intricate, involving a global community of scientists and vast resources. Whether the ultimate outcomes of the Large Hadron Collider will simplify our understanding of the universe or just lead us into more complex scientific challenges is still to be seen. It's a dynamic process, with every experiment potentially opening up new avenues of inquiry, as well as providing answers that might confirm or challenge existing theories. The discovery of the Higgs boson, a key particle predicted by the Standard Model of particle physics, was a significant event in science. This model helps us understand how particles and forces interact, and it relies heavily on the Higgs boson to explain why things have mass. Imagine a celebrity walking into a party and attracting a crowd, making it harder for them to move around freely. This is similar to how particles gain mass. They move through the Higgs field that fills the universe, and their interactions with this field give them weight. The Higgs boson is a small signal of this field's presence. When scientists at the Large Hadron Collider at the European Organization for Nuclear Research detected this particle, it wasn't just a technical victory or a match to theory. It confirmed long-standing predictions. This discovery, often portrayed as revolutionary, actually affirmed what many scientists had long expected. While the finding of the Higgs boson was crucial, it was less about discovering something entirely new and more about confirming our existing theories. This raises a point about how science often progresses. There's excitement in confirming what we predict, but does this approach focus too much on validating what we know instead of exploring what we don't? The efforts to find the Higgs boson, involving thousands of scientists and vast resources, demonstrate a commitment to proving theories. However, one could argue that such intense focus on expected outcomes might limit the pursuit of more uncertain and potentially groundbreaking ideas. Moreover, the description of the Higgs as the God particle is often used to make the concept more thrilling to the public. While this makes the idea more accessible and engaging, it may also oversimplify or overly dramatize the particle's role in our understanding of the universe. Science is a process of continual questioning and discovery, where each answer leads to new questions. In looking at the broader picture, the confirmation of the Higgs boson is a step forward, not an endpoint. It's important because it supports the framework we use to understand the physical world. Yet, this should be seen as a foundation for further questions and research, not a final answer. The unknowns remain exciting for physics, areas where the standard model doesn't give us answers. These gaps are where future scientific breakthroughs are likely to occur. Now, let's see how the Higgs boson discovery changes our understanding of the universe and the way we do science. The desperate hunt for the Higgs boson. Considering the impact of the Higgs boson's discovery, we should also reflect on how science is conducted. The focus on collaborative international projects, like those at the Large Hadron Collider, shows the power of collective effort in science. Yet, we must also ask if our scientific culture, which often emphasizes confirming theories, may overlook more speculative research that could lead to novel discoveries. The search for the Higgs boson was like looking for a needle in a haystack, but on a much grander scale. This important but incredibly short-lived particle could only be detected under very high energy conditions. Once created, it fell apart into other particles almost instantly. Scientists had to detect these other particles and figure out that they came from a Higgs boson. This task involved not only a deep understanding of particle physics, but also incredible precision in the technology used. The challenge was enormous. The detectors at the Large Hadron Collider were tasked with capturing and analyzing billions of particle collisions. Just imagine the overwhelming job of sorting through all that data to catch a glimpse of the Higgs boson. The energy levels required were so high that they pushed the Large Hadron Collider to its operational limits. Additionally, picking out the Higgs signal from the multitude of other particle interactions demanded new techniques in data analysis and interpretation. Every potential detection of the Higgs had to be examined thoroughly to confirm it wasn't an error or a case of mistaken identity. So why is the discovery of the Higgs boson important? This breakthrough confirmed a theory that had been around for almost 50 years and opened new ways to understand the universe. The Higgs boson is crucial to the standard model of particle physics, which explains everything in the universe except gravity. This model says that the Higgs boson is connected to the Higgs field, an energy field that exists everywhere in space. As particles move through this field, they gain mass. Without the Higgs field, particles would move at the speed of light, making it impossible for atoms, stars, planets, and life as we know it to exist. Finding the Higgs boson filled a major gap in the standard model and strengthened its foundation. It proved that the Higgs field isn't just a theoretical idea, but a real factor affecting the structure of the universe. But what does this mean for us? Even if the Higgs mechanism were unproven, the physical world around us wouldn't suddenly disintegrate. However, this discovery does more than just confirm old theories. Knowing the mass of the Higgs boson opens up new areas of physics, potentially leading to breakthroughs as significant as those brought about by quantum mechanics and relativity. But despite the huge amount of public money and effort spent on these massive detectors and the particles they hunt, the direct benefits of this high-level physics are not immediately clear to most people. The immediate practical relevance might appear remote, confined to theoretical discussions rather than everyday applications. Yet, the quest for understanding continues, fueled by human curiosity and the persistent drive to acquire knowledge. It's an expensive, complex venture with benefits that might seem elusive at first glance. Nonetheless, this exploration pushes forward, motivated by the desire to know more about our universe, how it works, and our place within it. Each discovery, no matter how abstract it might seem, adds a piece to the puzzle of our cosmos, slowly building a clearer picture of the reality we inhabit. The Higgs boson is lighter than expected. Normally, we would think it would be heavier because of the way it interacts with other particles. This unusual lightness suggests there might be parts of physics we haven't discovered yet. This leads scientists to explore even deeper questions, like what dark matter is and whether there are other dimensions we don't know about. Dark matter is a type of of matter that makes up about 27% of the universe. It doesn't emit, absorb, or reflect light, so we can't see it directly. We only know it exists because of the way it affects the movement of galaxies and clusters of galaxies. Scientists think that studying the Higgs boson might help us find new particles that could tell us more about dark matter, or even show us surprising things about the universe, like the existence of parallel universes and the strange phenomenon of the Mandela effect. The discovery of the Higgs is also important for understanding the early universe, right after the Big Bang. During this time, the universe expanded very quickly in something called inflation, and the Higgs field might have been involved in this process. By studying the Higgs boson in experiments like those done at the Large Hadron Collider, scientists can learn about what the universe was like soon after it began, which helps us understand how it has changed over time. Next, we explore how the Large Hadron Collider helps us uncover the building blocks of the universe. The explorations at the edge of space and time. The Large Hadron Collider is like a time machine in that it lets scientists recreate the conditions of the early universe moments after the Big Bang. By doing this, they hope to learn how the universe's building blocks came together. One of the most thought-provoking ideas in physics is the multiverse theory. This suggests that our universe might be just one of many different universes, each possibly having different laws of physics. This idea came from combining thoughts from quantum mechanics and theories about how the universe expanded right after the Big Bang. In this model, different parts of space might have stopped expanding at different times, creating many separate bubble universes. The Large Hadron Collider could help us understand if the multiverse theory might be true. It does experiments that look for signs of extra dimensions and unusual particles. If gravity can move between our universe and others through extra dimensions, we might be able to detect this at the Large Hadron Collider. Also, finding tiny black holes at the Large Hadron Collider would be a big deal because it could mean that there are more dimensions than we can usually observe. Studying the Higgs boson at the Large Hadron Collider could also tell us about these other possible universes. If the properties of the Higgs boson, like its mass, seem particularly suited to supporting life only in our universe, it could mean that other universes have different physical laws where life as we know it couldn't exist. The Mandela effect is another interesting topic. It refers to when many people remember the same event differently from how it actually happened. Some people think this could be evidence of parallel universes affecting our own. While the Large Hadron Collider mainly studies particle physics, its work exploring dimensions and fundamental forces could indirectly help us understand if parallel universes might be real. The Large Hadron Collider also plays a crucial role in searching for dark matter. Dark matter doesn't interact with light or electromagnetic forces, which makes it invisible and intangible in a traditional sense. However, it's essential for explaining why galaxies rotate the way they do and why galaxies and clusters move as they do. The Large Hadron Collider tries to detect dark matter by looking for signs of it in high-energy particle collisions. Although dark matter particles would pass through detectors unnoticed, scientists can look for missing energy and momentum in the collision data that might suggest dark matter was there. This search is similar to looking for the shadow of an object rather than the object itself. Just like a shadow can tell us about the shape and size of the object casting it, the missing data in particle collisions can give us clues about the properties of dark matter. As we continue to explore these ideas, they constantly push the boundaries of what we know and challenge our traditional views of reality. Diving into the concept of dark matter, various theories suggest potential particles that the Large Hadron Collider might detect. Among these theories are the weakly interacting massive particles, which could interact with regular matter or transform into detectable particles. The Large Hadron Collider isn't just smashing particles together for the fun of it. It's carefully looking for any signs of dark matter, which might show itself by affecting the behavior of the Higgs boson, a particle believed to interact with all massive entities. If dark matter has mass, it's likely it would interact with the Higgs field. Understanding this interaction could shed light on whether the Higgs mechanism could lead us to discover more about dark matter. As the Large Hadron Collider's experiments become more sensitive and data analysis more precise, the chances of detecting subtle hints of dark matter increase. Some might say that this pursuit to pinpoint dark matter is more about testing our scientific tools and theories than discovering new aspects of the universe. With every experiment and analysis, researchers make small advances. Yet, what are we truly gaining from this? With this in mind, the European Organization for Nuclear Research has upgraded the Large Hadron Collider to create the high luminosity Large Hadron Collider. This isn't just a minor improvement, it's a significant step in the machine's ability. High luminosity means increasing the number of particle collisions. By doing this, the High Luminosity Large Hadron Collider will gather data faster, catching rare events that were previously too sporadic to observe. This increase in data is expected to give us better quality observations, potentially bringing to light new phenomena or providing solid data needed to support or challenge current theories. The High Luminosity Large Hadron Collider has ambitious aims. It plans to delve deeper into theoretical spaces, looking for evidence of dark matter, exploring the possibility of extra dimensions, and investigating other phenomena that might explain the basic elements of the universe. The High Luminosity Large Hadron Collider also aims to measure the properties of the Higgs boson more accurately. These measurements are key to exploring the edges of the standard model and possibly discovering new physics. Reaching these goals isn't just about causing more particle collisions. It involves major improvements in the technology used to detect and process data. Upgrades are being made to the ATLAS and CMS detectors, which are vital to the Large Hadron Collider's experiments. These include new sensors and electronics that can handle higher levels of radiation and record data faster than before. For example, new tracking detectors being installed at both ATLAS and CMS are crucial for tracking the paths of charged particles after collisions. These new systems are designed to be more detailed, helping to distinguish important events from the regular background noise. However, one might wonder, with all these upgrades and the constant flow of data, are we truly getting closer to understanding the universe? Or are we merely chasing after theoretical shadows, hoping they might turn out to be substantial? As the Large Hadron Collider moves forward, it's hard to tell if we are uncovering new truths about the universe or just confirming what we already believe. With new upgrades, the High Luminosity Large Hadron Collider takes us even closer to understanding deep physics. The high stakes of high luminosity. The process of advancing our knowledge about the universe through the Large Hadron Collider is a gradual one, involving numerous incremental steps. Each bit of data, each experiment, adds a small piece to the vast puzzle of the cosmos. The hope is that, over time, these pieces will come together to form a clearer picture of the universe. However, the complexity and subtlety of the data we're dealing with mean that every discovery leads to new questions. It's a continuous cycle of hypothesis, experiment, and revision. The HL Large Hadron Collider's enhanced capabilities mean that we can now probe areas of particle physics that were previously out of reach. This could lead to breakthroughs in our understanding or confirm that our existing theories are on the right track. The of discovery is slow and filled with technical challenges that require not just new machines, but also new ways of thinking about the data we collect. As the High Luminosity Large Hadron Collider paves the way for future discoveries, the scientific community watches eagerly, ready to interpret its findings and ponder their implications for our understanding of the universe. As the High Luminosity Large Hadron Collider gears up for its next set of experiments, it's clear that both immense opportunities and concerns are part of the package. The collider's latest upgrades are designed to track particles more accurately, allowing scientists to better analyze the debris from particle collisions. This is essential for making sense of complex subatomic events, which would otherwise be like trying to understand a movie by only watching the final scene. These hardware improvements are crucial, but only part of the story. The bigger issue is dealing with the expected surge in data. Current computers are already struggling to keep up, and with more data expected from the High Luminosity Large Hadron Collider, there's a real need for a solid plan to handle this overflow. Artificial intelligence and machine learning are stepping up to this challenge. These technologies are being tailored to sift through massive amounts of data to spot important patterns and unusual results that could signal new scientific discoveries. The ability of these systems to manage, analyze, and make sense of large datasets quickly and accurately is not just helpful, it's critical. Quantum computing promises to process data at speeds that are currently out of reach for traditional computers, offering a potential solution to the growing computational demands. However, the full application of quantum computing and data analysis is still more a hope than a reality. with practical uses still on the distant horizon. With every experiment and every piece of data analyzed, we inch closer to understanding the deeper truths of our universe. However, this scientific quest is not just about discovering new things. It also brings to the forefront a range of ethical concerns and public worries. The powerful collisions within the Large Hadron Collider generate not only scientific interest, but also serious safety concerns. The notion of creating micro-black holes, despite being debunked by scientists, has captured public attention and stirred fears. Although theoretical predictions assure us that these black holes would vanish almost immediately due to a process called Hawking radiation, the very idea of creating them on Earth can be unsettling. The European Organization for Nuclear Research has responded by conducting thorough safety studies and collaborating with leading physicists to address any potential dangers. These studies affirm that micro-black holes, if they were to be created, would pose no threat, as they would dissipate too quickly to cause any damage. Despite these reassurances, the public's fear is not easily alleviated, raising questions about whether these explanations are sufficient or merely meant to calm fears, rather than provide detailed understanding. The path of discovery at the High Luminosity Large Hadron Collider is paved with both scientific excitement and a web of practical and ethical dilemmas. As we delve deeper into the fabric of the cosmos, we must also navigate the complexities of managing huge data volumes, addressing public concerns, and ensuring ethical research practices. Each step forward is closely watched by a concerned public, adding layers of responsibility to the scientific community's quest for knowledge. As the Large Hadron Collider continues to push the boundaries of what we know about the universe, it also tests the boundaries of what we can manage in terms of data and public perception. Balancing these aspects is as much a part of the scientific process as the experiments themselves. The ongoing dialogue between European Organization for Nuclear Research and the wider community is crucial to maintaining trust and understanding as we explore the fundamental forces that shape our universe. The European Organization for Nuclear Research often talks about being open and transparent about the high-energy particle physics experiments it runs. They emphasize this commitment through several public outreach and educational programs meant to explain their work and its possible impacts. European Organization for Nuclear Research also says it follows tough international safety standards, watched over by scientists and safety experts from around the world. Yet, there's room to question how sincere these efforts are. The information shared through these programs can sometimes seem more like a public relations move, aimed more at calming the public's worries than fostering real understanding. The details shared often focus more on the positives, glossing over any potential negatives. The insistence on following strict safety protocols and having constant monitoring might appear to be good, but it could also be seen as an attempt to soothe fears about the risks involved in these experiments. These risks are real and could lead to unexpected outcomes, despite all the precautions. There are also ethical issues that don't always get enough attention. For instance, running such a huge facility has a significant environmental footprint due to the large amount of energy it uses. There's also a debate about whether the money spent on particle physics is worth it. Some people argue this money could be better spent on solving more immediate problems, like poverty or improving healthcare. Let's look at the real-world impacts and challenges of conducting high-level physics research, the price of pushing dangerous boundaries. Moreover, there's a question about the necessity of the knowledge gained from these experiments. Understanding the smallest parts of the universe is certainly an impressive goal, but it's worth considering whether these scientific advances will help solve the critical issues that people face today. This situation places the European Organization for Nuclear Research in a tricky position, caught between its aim to expand human knowledge and the need to justify these expensive projects in a world with many pressing needs. Furthermore, the ethics of prioritizing research that may not have practical outcomes soon is a contentious topic. When so many worldwide suffer from basic needs, the allocation of vast resources to theoretical pursuits can seem out of touch with global priorities. This highlights a fundamental dilemma: the balance between advancing scientific understanding and addressing immediate human conditions. These concerns suggest that while the European Organization for Nuclear Research's work is groundbreaking, it is also surrounded by questions about its true cost and value. The discussion about whether the potential scientific breakthroughs justify the enormous expenditure and environmental costs continues, reflecting broader societal debates about the role and responsibilities of science in addressing real-world problems. The prioritization of scientific projects often sparks intense discussions both inside and outside the scientific community. The European Organization for Nuclear Research tries to calm these debates by ensuring its experiments are justified scientifically while also meeting ethical and environmental standards. The organization carries out environmental impact studies and looks for ways to cut down on energy use and waste, although one might wonder if these efforts are truly effective or just surface-level gestures to appease environmental concerns. The impact of the Large Hadron Collider at the European Organization for Nuclear Research is said to reach far beyond particle physics, touching various other areas of science and technology. While discoveries at the Large Hadron Collider are often celebrated as groundbreaking and capable of radically changing our understanding of the universe, there is a hint of skepticism about how these findings translate into real-world benefits. These discoveries are supposed to pave the way for new technologies that could change everyday life, but the actual advantages for ordinary people seem vague and distant, stuck in a realm of what could be rather than reality. Critics point out that the enormous amounts of money spent on such massive projects could instead be used to address more immediate human needs, such as health, poverty, and the environment. Moreover, while the Large Hadron Collider is seen as a symbol of scientific achievement in theoretical research, it also represents a huge investment of resources with outcomes that have little effect on practical technology. The challenge of balancing the pursuit of basic science with the development of useful technologies that benefit society remains a contentious issue. Despite the European Organization for Nuclear Research's claims of conducting responsible scientific research, the broader impact of its activities brings a mixed response of respect and criticism. The story of pioneering research linked with social progress is persuasive, yet the actual scenario is a patchwork of hefty investments with slow and often unclear results. This situation leaves some questioning whether the thrill of unlocking the universe's oldest puzzles justifies the massive spending. On the environmental front, while the European Organization for Nuclear Research engages in measures to reduce its footprint, the sheer scale of its operations and the energy-intensive nature of experiments like the Large Hadron Collider raise concerns about their sustainability. The optics of committing to environmental stewardship contrast sharply with the reality of its substantial energy demands, creating a paradox that is not easily resolved. Regarding technological advancements, the indirect benefits touted by such research initiatives often manifest slowly and are usually confined to specialized industries before they trickle down to general public use. This delayed gratification is a tough sell to those who fund and observe from the sidelines, hoping for more immediate returns on their investments. The World Wide Web, now essential for global communication, started at the European Organization for Nuclear Research in 1989, designed originally to help physicists share information. What began as a tool for a small group has expanded massively, becoming vital for almost every aspect of modern life. This leap from a niche invention to a global necessity is a prime example of how specialized scientific ideas can evolve beyond their initial purposes. However, the spread of such technologies brings mixed outcomes. While the internet has opened up access to information, it has also become a channel for spreading false information and a tool for excessive surveillance. These developments prompt a careful consideration of the broad impacts of technological advancements beyond their immediate benefits. In physics and engineering, technologies developed for the Large Hadron Collider at the European Organization for Nuclear Research have been adapted for medical use. For example, superconducting magnets and sophisticated vacuum systems, which were initially created to explore fundamental particles, are now used in advanced medical imaging techniques and treatments. This includes improvements in cancer therapy with proton beam therapy, which targets tumors precisely, minimizing harm to surrounding healthy tissue. However, such technological transfers also raise questions about the costs and priorities of public investments. The movement of technologies from particle physics to everyday applications isn't just a success story. It also involves debates over how money is spent and what should be prioritized by governments and institutions. European Organization for Nuclear Research's intense need to process vast amounts of data has also led to breakthroughs in distributed computing, which now help in areas ranging from predicting climate change to mapping human genes. These advancements in handling large data sets are certainly beneficial, but they also bring issues such as data privacy concerns, the concentration of technical power in a few hands, and the risk of increasing the divide between those who have access to advanced technologies and those who do not. Looking ahead, the European Organization for Nuclear Research is planning to construct the Future Circular Collider, an ambitious new project designed to delve deeper into the structure of atoms. This collider would span approximately 62 miles in circumference and reach energy levels significantly higher than those of the Large Hadron Collider. The facility is anticipated to uncover new particles and offer more profound insights into the nature of dark matter. What are your thoughts on the potential risks of increased data privacy breaches with such technologies? Like, comment your views, and don't forget to subscribe for more discussions.